Black hole. A black hole is formed when a very massive star runs out of nuclear fuel and collapses under its own gravity. The core compresses so extremely that gravity becomes so strong it traps even light, which is why black holes appear completely dark. Black holes vary greatly in size. Stellar black holes can be only 12 to 60 miles wide, while supermassive black holes can grow larger than the entire orbit of Neptune. The black hole at the center of our galaxy is about 14 million miles wide, meaning the whole solar system could easily fit inside it. There is no atmosphere like a planet, but a black hole is surrounded by an accretion disk made of gas and dust spinning at speeds over 100,000 miles per hour. Friction heats this material to tens of millions of degrees Fahrenheit, making it one of the hottest regions in the universe. If a human comes close, gravity does not pull the body evenly. The lower part of the body is pulled much harder than the upper part, stretching the human vertically. Blood vessels rupture, organs tear apart, and the brain quickly loses oxygen. Consciousness fades long before the human reaches the event horizon, and death occurs before the body is fully pulled inside. Neutron star. A neutron star forms after a massive star explodes in a supernova, but does not become a black hole. Instead, the core collapses so intensely that protons and electrons merge into neutrons, creating one of the densest objects in the universe. A neutron star is only about 12 to 15 miles wide, making it far smaller than Earth, yet it contains more mass than the Sun. If placed in the solar system, it would be smaller than a city, but heavier than all planets combined. Surface temperatures can exceed 1,800,000 degrees Fahrenheit, and the atmosphere is extremely thin, made of ionized particles trapped by magnetic fields, trillions of times stronger than Earth's. These magnetic forces drive intense radiation and particle winds moving at enormous speeds. If a human comes close, gravity alone would crush bones and organs instantly. At the same time, the magnetic field would disrupt electrical signals in the nervous system, stopping brain activity almost immediately. The human body would collapse and cease to function before any physical contact with the surface. White dwarf. A white dwarf is what remains after a sun-like star reaches the end of its life. When such a star runs out of fuel, it sheds its outer layers into space, leaving behind a small but extremely dense core. This core no longer produces energy and slowly cools over billions of years. A typical white dwarf is about the size of Earth, roughly 7,500 miles wide, but it can contain half to almost the full mass of the Sun. This means its density is so high that a teaspoon of white dwarf material would weigh several tons on Earth. Compared to planets in our solar system, it is similar in size to Earth, but far heavier than any planet. Surface temperatures can range from 180,000 degrees Fahrenheit when newly formed to below 10,000 degrees Fahrenheit as it cools over time. White dwarfs have no true atmosphere like Earth. Instead, they possess a thin layer of hydrogen or helium above an ultra-dense core. There are no winds like on planets, but gravity at the surface is about 100,000 times stronger than Earth's. If a human comes close, this gravity would pull the body downward with immense force. Blood would be forced out of the brain, bones would collapse under their own weight, and the body would be crushed flat in seconds. Death would occur almost immediately due to extreme gravitational pressure. Magnetar. A magnetar is a rare and extreme type of neutron star formed after the collapse of a massive star in a supernova. What makes a magnetar special is its unbelievably powerful magnetic field, the strongest known in the universe. Magnetars are only about 12 miles wide, smaller than many cities, yet they contain more mass than the Sun. Compared to planets, a magnetar is tiny, far smaller than Earth, but its mass and energy output surpass anything found in the solar system. Surface temperatures are typically around 1 million degrees Fahrenheit, and the atmosphere is extremely thin, composed of ionized particles locked in place by the intense magnetic field. Magnetars can release sudden bursts of energy called starquakes, sending radiation across space. These eruptions travel at the speed of light, about 670 million miles per hour. If a human comes close, the magnetic field alone would be deadly. It would disrupt the electrical signals in the nervous system, stop the heart, and tear molecules apart by rearranging atoms inside the body. Even from thousands of miles away, the magnetic forces could cause fatal damage. Death would occur almost instantly without any physical contact. Supernova. A supernova occurs when a massive star reaches the end of its life and explodes violently. This happens when the star can no longer support itself against gravity, causing a catastrophic collapse followed by a massive explosion. The explosion can expand across distances far larger than the entire solar system, releasing shock waves, radiation, and heavy elements into space. Temperatures during a supernova can exceed 1 billion degrees Fahrenheit. There is no atmosphere, only expanding plasma and radiation traveling at tens of thousands of miles per second. Supernovae are responsible for creating many of the elements found on planets, including those in the human body. If a human were anywhere nearby, the intense radiation and shockwave would vaporize the body instantly. Even at greater distances, radiation exposure would destroy cells and organs, leading to death shortly after. Gamma ray burst. A gamma ray burst is the most powerful explosion known in the universe. It forms when a massive star collapses into a black hole, or when two neutron stars collide. In just a few seconds, a gamma ray burst releases more energy than the sun will emit in its entire lifetime. The radiation beam from a gamma ray burst can be wider than an entire solar system and travels at the speed of light, about 670 million miles per hour. It has no atmosphere, no visible structure, and no warning signs. It is pure high-energy radiation moving through space. Temperatures during these events reach extreme levels that cannot be measured normally, as energy output is far beyond stellar processes. Even from thousands of light years away, gamma-ray bursts can damage planetary atmospheres. If a human is exposed, gamma radiation passes straight through the body, tearing DNA apart inside every cell. The nervous system shuts down instantly, organs fail at the molecular level, and death occurs before the brain can register pain. A star like the sun. Stars form when massive clouds of gas collapse under gravity and ignite nuclear fusion in their cores. Our sun is a medium-sized star, yet it is still enormous compared to planets. It is about 864,000 miles wide, meaning more than 100 Earths could fit side by side across it. The sun has multiple atmospheric layers, including the photosphere, chromosphere, and corona. Surface temperatures reach around 10,000 degrees Fahrenheit, while the core burns at approximately 27 million degrees Fahrenheit. Solar winds constantly stream outward at speeds up to 1.8 million miles per hour. Unlike planets, stars have no solid surface. They are massive spheres of superheated plasma held together by gravity. If a human comes close, intense radiation would destroy skin and organs long before reaching the surface. As heat increases, proteins in the brain break down, shutting down the nervous system. The body turns into plasma within seconds, causing instant death. Rogue Planet. A rogue planet is a planet that has been ejected from its original star system due to gravitational interactions. These planets drift alone through space without a star to provide heat or light. Rogue planets can be Earth-sized or even larger than Jupiter. Without a star, surface temperatures can drop below minus 370 degrees Fahrenheit. Some may retain frozen atmospheres made of nitrogen, methane, or hydrogen, while others lose their atmosphere completely. There is no sunlight, no seasons, and no external energy source. Any winds that exist are extremely weak due to lack of heat. If a human is exposed, extreme cold causes blood to freeze, organs to shut down, and brain activity to stop due to hypothermia. Death occurs slowly but inevitably in the silent darkness. Extreme time dilation regions. Extreme time dilation occurs near objects with enormous gravity, such as black holes and neutron stars, where space and time themselves become distorted. These regions are not physical objects, but effects caused by intense gravity. Time dilation zones can extend across areas larger than planetary orbits. There is no stable atmosphere, and physical laws behave differently compared to Earth. Temperatures depend on the nearby object, but are usually extreme. In such regions, gravity interferes with normal biological processes. If a human enters, blood circulation becomes unstable, neurons misfire, and cells stretch as space itself stretches. As molecular bonds break down, the body becomes incapable of maintaining structure. Consciousness fades slowly, and death occurs as the human body can no longer function within distorted space-time. Vacuum of deep space. Deep space is not cold or hot by itself. It is almost completely empty. There is no breathable atmosphere, no air pressure, and no protection from cosmic radiation. Temperatures can range from about minus 455 degrees Fahrenheit in shadow to 250 degrees Fahrenheit in direct sunlight. Unlike Earth, which has a thick atmosphere to regulate temperature and protect life, space offers no insulation and no oxygen. There's also no wind, but radiation particles move freely at extremely high speeds. If a human is suddenly exposed to the vacuum, air rushes out of the lungs, making it impossible to breathe. Oxygen supply to the brain stops within seconds, causing rapid loss of consciousness. Body fluids begin to boil due to low pressure, not heat, causing swelling and internal damage. Within 1 to 2 minutes, the brain suffers irreversible damage due to lack of oxygen, and death follows quietly without any dramatic explosion or freezing.